In this session, we're going to talk about some special probability distributions that we often use. We will make a brief introduction, then we will talk about the discrete probability distributions, namely binomial, negative binomial, geometric, and Poisson distributions. Then we will continue with continuous probability distributions, where we will talk about the uniform, exponential, gamma, Weibull, and normal distributions. And finally, we will conclude the chapter with the normal approximation to binomial distribution. The idea is the observation of many events in nature show that they bear the signs of specific probability distributions. The most common one is the bell curve, I think. You're familiar with it from your, grade distributions at classroom or something like this, and many things in nature as well. But of course, there are other distributions as well, like the binomial trials, where you talk about the, tossing of a coin or something like this. The discrete probability distributions are based on countable integer type variables. That's the idea. And now let's start with the binomial trials and binomial distributions. Those trials, binomial trials, are based on two possible outcomes of an event. For example, a coin toss, or a yes or no question, or a true or false question, or whether a patient is a smoker or not, or whether a device is broken or still functional, etc. So as you see, we're talking about two possible outcomes of an event here. Those are called, regardless of the probability of those occurrences, they do not need to be equal, but two possible outcomes are clear here. And the properties of binomial distributions are as follows, and your experiments are usually repeated for n trials, so they should be repeated. And only one of the two possible outcomes, namely the positive and negatives, can be observed in each trial. We will be curious about the positive ones, what we're seeking. They can change. And probability of the positive is given with small letter p, is the same for each experiment, where the probability of negative outcome, which is denoted with q, is its complement in the sample space, which is q equals 1 minus p here. We also consider that those experiments, all of them, are independent of each other. So your first trial will not affect the next trial, second or third trial, or something like this. And the main focus is the random variable capital X here, which is the total number of occurrences of those positive results that we're curious about. For example, the number of heads in n number of coin tosses. Although it is hard to observe binomial events precisely in real, it may not be possible. As long as the bias of this mechanism is low, if we have a nature like this, it's a useful model for specific occasions in nature as well. For example, suppose that you have 5,000 people in your data set, which consists of 2,500 smokers in it. When you make a random selection here, like a sampling from this one, the probability of getting a smoker in the first trial is, of course, 1 over 2. But in the second trial, precisely, it would be 2,499 over 4,999. This would be the probability of getting the second smoker. But in fact, this is not a significant difference in p-value. That's the idea about those assumption in the bias here, what we have here. But it is not applicable in small populations unless we change the nature of the experiment to satisfy the condition of binomial trials. So if you have if you have many elements in your population, or many members of your population, that would be all right. But if you have, for example, 10 members in your population, then you need to do some manipulation to fit it into a binomial trial. What would you do? For example, the most straightforward one is just replacing it. Okay, you choose one of the person from that sample set, then you replace him again in the sample set. As like for example, in our example of smokers, for example, you will always deal with sampling from 5,000 people. You can assume like this. Or, for example, putting the balls back before each trial. Suppose that you have several number of balls in a bag or something, limited one, and a small number of balls. And for each draw, you replace the previous one to push or you force your experiment into a binomial trial. The independency of trials also have to be secured by some manipulations. For example, suppose that you're curious about the scoring percentage of a basketball player, scoring capability for field goals, for example. How would you enforce or achieve independency of the trials here? What would you do? Just pause the video and think about it for a while. So the idea is, what can we do is, for example, we can change the positions, their locations of those shots, and we can also make the shots in different times, at different days of the week and at different times of the day or something. What we're trying to do is trying to achieve the independency of each trial from each other. That's the idea. Otherwise, suppose that you're shooting from the same location after and over and over, if I make 20 shots from the exactly the same point in, let's say, 5 minutes, eventually the trials will be dependent on each other because I will get better and better with each shot, right? So that's why the achievement of independency between trials is also important, and if it is not naturally available, you can enforce or you can do some manipulations to achieve that independence. This is important, So when we consider that we have n as the number of trials and x is your random variable, is the total number of occurrences of those positives here, for n equals 1, it means that you will have only one trial. Your x would be either x equals 1 or x equals 0. That's it. You either have positive or negative. These are the total number of positives here. It would be 1 or 0 depending on your outcome. Let's do it a bit together. So here you will have for n equals 1 for random variable x here, and those will be your events, the negative and the positive, which would give you 0 and 1 in total, and the probability of those getting those totals will be consecutively q and p. And when you add them up, not surprisingly, you will come up with 1, of course. So that's the idea. And Suppose that you have two trials here. Then what happens? I think we're familiar with this from the previous chapter here where we talked about probability as well. You can either have negative negative, or negative positive, or positive negative, or positive positive, right? That's it. And what would be the number of total x here that we're curious about? The number of positives, remember, it would be 0 and 1 and 2 in the trials, remember from the coin toss. And the probability of x would be q times q, q times p plus p times q, and p times p. Those would be the probabilities which would make up q squared, 2pq, and p squared. Again, pretty similar to this. If we add all of these together, so your sum of all those probabilities give you p plus q squared, which would be equal to 1, not surprisingly. And if you have, for example, again, 3 events here, what happens? Now, here in this sense, you will have this one. Those will be your events, this one, and plus, minus, minus, and minus, plus, minus, and minus, minus, plus, and plus, plus, minus, and plus, minus, plus, and minus, plus, plus. Okay, and you will have 3 positives as well. So if you have 3 trials here, not surprisingly, you will have those values available, and their corresponding probabilities will come out as q, q, q. So you see p, q, q plus q, p, q plus q, q, p, and p, p, q plus p, q, p plus q, p, p, and p, p, p. Okay, like if you add them up, like this is okay, it's q3, and this is 3pq squared, and this is 3p squared q, and this is p cube. So you see, when you add all of these together, you will eventually have probability of x equals p plus q to the power 3, which is again 1. You see the pattern here. That's it. That's what we're looking for. And if we generalize this, we will come out with something like this, for where your n is the number of your trials. That's the idea. So for any term, if you remember from our previous chapter, which where we talk about the combination here, these are the coefficients of binomial trials. Maybe you remember from our previous lecture. So you will have this combination as your coefficient, and probability of x over q for, okay, the remaining probability here, you see, and that would be valid for any term you're looking for here. And what was this one? I hope you remember this from the previous chapter. It is combination of n r, where you have it something like this, right? R factorial n minus r factorial here. You see this one. So what you have here is, again, like when you add them up, probability of x here, x power x, p x, q, n minus x, would give you p q over n. And since our q is 1 minus p, right, so it would be 1 plus 1 minus p over n. See these go, and you will have 1 over n equals 1. So that's what we're dealing with, and when you generalize this, you can achieve probability of x equals x, any term here, which would be n probability of qn minus x, where your x can take any value here up to n, because you will have n trials. This is called the probability distribution function of this phenomenon. Now we're going to continue with some examples here. Okay, let's continue with one example from our textbook. Suppose that there are 4 ambulances in a town, in a particular town, and they are moving independently, or they're working independent from each other. And this is the probability of being ready at any given time, for being ready for emergency call. For at any given time, the probability of an ambulance being ready when an emergency call comes, it's 80%. So what we're curious about in the first part is only 2 ambulances ready at a particular time. If you get a call, what is the probability of this one? You're curious about the probability of this element, or this one. Here you have, see that your n is 4. How do you know? Because you will have 4 ambulances for this one, and the probability of your p is, what you're curious about, is 80%. And of course, the being not ready is the complement of it, right? It's 0.2. And the probability of x equals x was what? We had a formula for this, right? Or like it is x, and this is the q, your probability of q here, and 4 minus x here. And you can replace any number here with this variable, like for example, you will have 4, 2, and you will have 8, 2, and 2, and 2, right? Because 4 minus 2 is 2 here. When you make the necessary calculations with your calculator, you will come out with, okay, let me write this as final step 2, just to make some exercise with you as well. 0.04. So the result will be like 15% or something like this, around 15%. This is the answer to part A of the question. And part B of the question asks at least 2 ready, probability of let me write this clearly, probability of at least 2 ready ambulances at any given particular time, at least 2. Now, what we're dealing here is, please try to understand the problem as well as possible first before you start solving. What we're trying to do here is anything greater than or equal to 2 here. That's what we're trying to find out. Probability of 2 plus probability of 3 plus probability of 4, which is your maximum, right? You have 4 ambulances ready at all. You can write this from subtracting from 1 as well, because when you add them up, you would get 1, right? Probability of 1 minus probability of 0. This is more efficient than this one, because here you calculate 3 probabilities. Here you calculate only 2 probabilities here. So we will choose, and the author also chooses the second alternative as well, and it would give you 1 minus 4, 0.8 over 0 times 0.24 minus 0. This corresponds to this one, okay, for the 0. And you will have another minus here, which is 4 combination 1.81, 2, 4 minus 1, okay, and this corresponds to which one? This one, right? So that's the idea. And your result will be, when you make the necessary calculations, it would be 0.9728, which is approximately 97% probability that 2 or more ambulances will be ready at any given time. And finally, the last one is all 4 of them ready. The probability of all 4 ready here. What would it be then? In our formula, we will put like this, right? So this is what we're dealing with, and combination of 4, 3 over 2, 3 over 4 minus 4, and it would give you 4 factorial over 4 factorial 0 factorial, right, coming from the formula or definition, and it is 0.2 over 0. When you make the necessary calculations with your calculator, it will come up with something like 40% or like this as the answered question in your part C as well. What else? And the next example is again another example from the textbook. What is the probability of guessing 8 or more sex of 10 newborn babies, right? Newborns. What is the probability of guessing 8 or more correct sex of the 10 newborn babies? Here you will have, if you have 10 newborn babies, your n is 10, and your x should be greater than or equal to 8, right? And what is the probability of occurrence here, or guessing? Q is, since your Q is 1 minus P as well, it's like a coin toss, right? Because it's like this in the nature. And what we're dealing with would be the probability of x greater than or equal to 8 would be probability of x equals 8 plus probability of x equals 9 plus probability of x equals 10, right? This is the most convenient one for calculation when we do this. So it would be 10.5 over 8 times 0.5 over 2 plus this time 10 combination 9, it's 9, 5 over 1 plus and 10.5 over 0. So the result will be, when you make the necessary calculations with your calculator, it is 0.055. So it's approximately like 5.5% probability or something like this. So suppose that you're trying to guess, or you're trying to calculate 80 correct guesses over 100, for example. Would this probability drop or increase? Just think about it, okay? Pause the video and think about it. And what we will tell us, we will see this, whether something extraordinary or ordinary happening here. We will discuss about this more in chapter 4 particularly, but this is the idea about the binomial distribution examples for now. And let's continue with the mean and variance of the binomial variable. So let me get a fresh board. So for any random variable, mu is your expected value of x here, and your variance will be your expected value of x minus mu squares, right? I think we know this from our previous chapter, the concept of expected value, right? I suggest you to review it if you want to remember, if you like. And for n equals 1, if your trials are 1, we're so this mean your mu, like x should be from x to 1 x px, which would be 0 times q plus 1 times p, right? If you have 1 here, so the result would be your p, your probability. This would be your expected value for one try. For n equals 2, you will have mu x from x equals 0 to 2, x times px, and it would be what? Should be 0 times q square plus 1 times, okay, your x is 1, times combination of power 1 q plus your 2 times p squared. When you make the necessary common parentheses here, q plus p, what you will have, see that this one is 1, right? So the result will be 2p. And for n equals 3, that will be mu be 3p. Okay, see the pattern here is making us perk, like 1, 2, and 3 here. And when we generalize this, your mu, which is your expected value of x, would be np. This is called the location parameter of the binomial distribution. Okay, this is what we call, or this is what we're dealing with in this sense. And let's talk about the variance of binomial variables here for n equals 1. Now what we're dealing with would be the variance. So the variance would be the summation of the sum of squares from the difference from the mean. from x equals 0 to 1, it would be x equals mu square px. Okay, this is how we do it, right? If you remember from the previous chapter, the concept of expected value here, 0 minus p squared times q plus 1 minus p squared times p. This will what we have, and it would be p squared q plus q squared p. When you take them in common parentheses, p times, oops, let me write this nicely, p times q, parentheses, q times p, this would be 1, right? So it should be pq. This is the variance. And for 2, for n equals 2, what happens? So again, this time it would be variance again, x minus m square x from 0. This time it is up to 2, right? That's it. X minus mu square px. And the result will be what? Let's write this here. 0 minus 2p square q square plus 1 minus 2p square plus 2pq plus 2 minus 2p square pq. But I hope you remember that our mu here, if your n is 2 here, your mu should be 2p, right? That's why we're putting 2p here. I think we already discussed this a few moments ago. So when we make this, we try to end up with something like this. Okay, it would be 4p square q square and plus 1 minus 4p plus 4p square and 2pq plus 4 1 minus p square p square, that's one. So when you try to write this one as since your 1 minus 2pq, considering that your q equals 1 minus p, right? Okay, just take a look at this. This one can be written like, if we use this one, q minus p square, right? And okay, this one we're talking about, this part. Okay, this one, let's focus on this one. And when we make the necessary the expansion here, we will end up with 4p square q square plus, let me use another color here, q square minus 2pq plus p square, I'm expanding this one, times 2pq here, coming from here, right? Okay, and you continue with the remaining part, 4q square p square here. Look at this one. This is also q, right? This is coming right here. And we will have 8p square q square plus 2p q q to the power 3 minus 4 p square q square plus 2 p to the power 3q, and the result will be 2 to the power 3q 4 p square q square plus 4p, this one. Okay, if we take them in two parentheses, I will go a bit slow, but that's all right. Q square q 2pq square plus pq to the power 3. Let's put here pq as well. Let's use pq as well here, and it would be 2pq in common parentheses. It would be p square plus 2pq plus q square. All right, I think this was what we're looking for, like p plus q square. And what is it? It is 1, right? So this would be 1, and the result will be 1, and we will be left with 2pq. So we can conclude that for n equals 2, your variance will be 2pq. Okay, for n equals 1, it was pq. For n equals 2, it will be 2pq. And if you're say motivated enough to calculate it for n equals 3 as well, you will eventually come up with this one as well, from if you want to prove it. Square will be, not surprisingly, 3pq. And if you generalize this, and it would be the variance of the binomial variables here, which would correspond to n, p, q here. That's it. And this is called the variance parameter of binomial distribution, or shape parameter, right? Variance parameter or shape parameter. And your location parameter was this one of your binomial distribution. So that's it about the binomial trials and distributions.